Welcome, everyone. I hope you enjoyed the Easter break. And today we're going to discuss the paper we did a few years ago on the past, present, and future of artificial life. And well, I'll give a brief introduction, and then we should discuss what you think about artificial life and its perspective for the near future. So, as it says in the paper, since antiquity, there were several myths about humans creating something like life. So this was also related to the idea of all these cultures also had creation myths. That's how different gods created the planets and the sun and the moon and humans and everything we could perceive. It seems it's a natural tendency of our species to have these explanatory narratives of why are we here. And together with these explanations comes the idea, well, if someone was able to create us, why shouldn't we be able to create something like ourselves? And many mythologies address this issue with different myths. And I mean, there were some rudimentary advances that we could call examples of artificial life, like automata. The beginning of the course, we already mentioned how the need for timekeeping in the age of exploration in the 17th and 18th centuries kind of pushed the development of clockworks, and then these clockworks were also used to develop automata, which were later called robots, and more sophisticated as technology advanced. And I mean, of course, now we can see very sophisticated robots, but also we can see some robots which fail miserably. I mean, there's a classic video of the Zimo robot by Honda a few years ago. And it's like a demonstration show, science museum, maybe in Mirai-kan in Tokyo. And he attempts to climb the stairs and just falls, and the curtain falls, and technicians run to try to fix whatever went wrong. Also, I mean, of course, it's not trivial to develop something like we observe in living systems, but still there has been several attempts, or well, I wouldn't say attempts, to say a systematic scientific effort since the 1980s to study life, not so much as it is, that has been the subject of biology, but as Chris Langton put it, life as it could be. Or also people like Stuart Kaufman speak about the general biology. So it means a biology that is not restricted to the biology we know, which is living systems in our planet, all of which are made of cells, all of which have very similar metabolism, all of which have DNA. So we have just one instance of biological life, but that doesn't mean that there couldn't be or there shouldn't be other instances of life. That's why it's called a general biology. And artificial life works on both sides, building artificial systems to try to understand biological systems, but also understanding biological systems to build artificial systems that have the properties of biology, such as adaptation, learning, development, resilience, self-organization, and so on. So there have been different applications out of artificial life, but let's say it hasn't become mainstream. However, the community still persists, and there are yearly conferences. This summer, there will be one organized by a group in the University of Trento, in Italy, but it will be also a hybrid conference or perhaps mainly online conference, just like the 2 previous years because of the pandemic. And we organized the conference with Confrese and several other colleagues in 2016 in Cancun. So, yeah, I mean, the first conference of artificial life I went to was in 2002. So I've been attending the conference now and then for 20 years already. I mean, I would like to listen to you. What did you think about the paper? What did you like? What do you fear? What do you dislike? Is it convincing? Do you find it suspicious? What are your thoughts on the field of artificial life? Is it useful? Is it just big boys playing God, or can it make a difference, or not?
Hi, Professor. Good morning.
Good morning.
I'm sorry for not being there. I have a little setback. But in my text, I really love the article because it explained the concept that I didn't know, the e-life. And I especially like the distinction between e-life and artificial intelligence. Also, the second order of emergency give me a lot of questions. And in my text, especially, I try to go deeper in the Gaia hypothesis of James Lovelock that is mentioned a little bit in the text when explain the Daisy World simulation and the ecological impact of e-life. And I also wanted to talk about the difference between e-life and robotics concerning the autonomy concept. So I was a little confused in these two distinctions. Because it mentioned that robots had to have an external operator. One should modify its behavior. And in that sense, I kind of thought that the planet Earth thought as Lovelock, it could be thought as a combination of e-life autonomy and robotics autonomy, in the sense that the planet Earth and its conditions, it's managed with the features of the whole solar system and the whole universe in a specific time scale that we can't see. But those features of the solar system have changed the Earth in several moments. It features its conditions and its intelligence organisms. Yep. So my proposal in my text is how it could be a combination of these two perspectives of autonomy, like combining e-life and robotics autonomy, that it could be achieved, or are two totally different views. that can be linked.
Yes, actually, artificial life, as it began in the 1980s, it started a bit in opposition to artificial intelligence because, well, if you remember in the history of artificial intelligence, say the term was coined in the 1956. Then in the 60s and 70s, there was like spring and summer, and then the winter came in the 1980s. And at the same time, there were several criticisms to artificial intelligence. Artificial life was one of them. Another one, which is very similar, but it's kind of a part of the community, called behavior-based systems, inspired more in ethology, was another one, and that had to do more with criticisms for robotics. And a third one was connectionism, or connectionism 2.0. So in the early 90s, there were big debates on whether the mind was symbolic or connectionist, meaning whether we have rules in our brains and process symbols, or whether it's just a massively parallel distributed computer. And of course, both metaphors are limited, but they also offer advantages. But I dealt with this for my master's thesis, and the conclusion is that in theory, you can build any connectionist systems with a rule-based system and vice versa, so they're computationally equivalent. So it doesn't really matter what really is, because anyway, there are both descriptions of the same phenomena, but with different purposes and at different scales. So the question should better be in which context each description is useful. So if we are very pragmatic, especially in robotics, in controlled environments, we just want the machine to do whatever we want the machine to do. We don't care so much whether it's biologically plausible, whether it's elegant. We just want it to work. And this led to the development of several robots, or earlier automata, that were not adaptable, and up to the point that many robots still nowadays, they are remote controlled, so they have zero autonomy. So, I mean, an example is one of these robots that disarms bombs. So of course you don't want humans going near bombs to defuse them. So they have built these little robots that they have arms, but let's say they're controlled by humans at a distance. So with a joystick and buttons and so on, like a video game, they control remotely the robots. So that, I mean, those are zero autonomy, but they're useful. Also, I believe there are some fighter jets which are remotely controlled, meaning that they don't have a pilot in the plane, but they are not autonomous. The pilot is somewhere else, and that's it. So if the plane is shot or there's an accident, then the pilot doesn't is not at risk. So that's like one extreme. And the other extreme that perhaps might be more interesting for artificial life is to have full autonomy, that it's like, okay, you build something and then you let it loose, and you expect it to have interesting behavior, whatever that may be. So those are like different perspectives with different purposes, and it would be difficult to say that one is better than the other independently of a context. So in some contexts, one might be preferable to the other. And related to Lovelock and looking at our planet, and well, any planet as a self-regulating system, I think it's a very interesting analogy because, I mean, as we saw with general system theory, we can use the same formalisms to describe phenomena at different scales. So if we understand better adaptive systems, even if it's with living systems, let's say with biological systems, and we see that our planet has similar homeostatic capabilities, then it's useful to understand better homeostasis in a general way rather than just at the level of organisms, but also at the level of ecosystems and biospheres. And moreover, when we are perturbing our biosphere in such drastic ways already for several centuries. So I think, I mean, I don't think we'll reach a level where we are able to control our planet like we control a robot, like with a remote control, because precisely it has its own autonomy and feedback loops and internal dynamics and so on, and, multiple scales. But I think we can aim at guiding. I mean, that's the idea of cybernetics, not to tell precisely a system what to do, which is actually what traditional robotics aim at. Like, okay, you have, I don't know, 6 different degrees of freedom, then you need to tell each motor how to turn. And this is, I mean, these type of problems explode combinatorically, and it's really almost impossible to control let's say a humanoid robot with such an approach. They just fall. I mean, just to keep balance. So alternative approaches that are based on adaptive systems are better suited because, let's say, you evolve or train the system to, for example, just to have balance. And I mean, if you have seen the videos of these Boston Robotics robots, that they have good balance and they can be pushed and they don't fall, it's precisely because they have these adaptive mechanisms inbuilt in them. And they're not trying to control precisely every little joint. They have, let's say, much more natural feedback loops, and also take the idea that the body is part of the controller. So depending on which body you have, it might be easier or not to control something. And I mean, you can easily see it when, for example, if you can't move some joints, so if you damage an articulation and then you need to put some cast on your leg or your arm or something, you notice that it's much more difficult to walk and keep balance and so on. So it's very similar. If you change the body, then the controller of simple things like walking become much more complex. And since evolution has co-evolved brains and bodies together, it makes sense that the bodies are easier to control. The bodies we have, well, and everything we perceive around, they're easier to control than what you might pick up randomly from the space of all possible bodies. So, yeah, I think there's much to be done in that direction. Any other comment?
Thank you.
Yes, Mauri.
Yeah. Well, for me, living beings are the most fascinating kind of matter in the universe because it's a bunch of information transforming, spreading, auto-organizing, adapting, and potentiating, evolving and reaching a level of maximum criticality and complexity that allow us create perception, conception, imagination, volition, emotion, all what we call cognition. And in fact, I think information is the most powerful way to understand life in all its facets. At the end of the text, the authors mention 14 open problems in a life, and the number 10 is develop a theory of information processing, information flow, and information generation for evolving systems. And as a matter of fact, information integration theory is the most adept framework to understand information processing. I mean, the amount of experimental data based on this theory is amazing, incredible. On the other hand, we have assembly theory, a new approach to understand information flow. And with this tool, we can characterize the complexity of living beings using information and not a particular ingredient or feature. And what we need now is a frame that allows us to understand the creation of information. In my opinion, rewrite the laws of thermodynamics in terms of information could be one possible way to understand the creation of information. But I want to know if you recognize another framework that allow us to explain information generation.
Yeah. A few years ago, there were several works related to something called synergistic information, which is, say, the amount of information that you get not from one source nor the other, but when you have both together. So, that's why it's called synergistic. So it could be seen a little bit like measure of emergence. So the information that you get when you put together two variables that you can't get when you have them separate. And there were several attempts for this, but it seems none of them was convincing enough because, let's say, they all kind of seemed good enough for some cases, but there were always counterexamples where they wouldn't be so applicable. There's also transfer entropy, which you can see it as an asymmetric version of mutual information. So that's already one step forward because, let's say, mutual information is symmetric, so it's the same from one variable to the other, and transfer entropy isn't. So it's the amount of information that you get from one variable when you have information about another variable. And at the end, there's this classic book of Judah Perl on causality, and he tries to define a bit causality in terms of information, but I tried to read it and I didn't understand it. And I haven't met anyone who has, so it might be that he has some deep concepts, but if no one understands him, then it's not very useful. I mean, what I want to say is that it doesn't solve the problem of differentiating correlation from causality. I think that many of these questions are related to meaning, and most approaches to information, they kind of try to take an objective perspective, and this from Shannon's first paper on this mathematical theory of communication. And there he says, well, of course you need like a meaning, let's say, that it's agreed between the sender and receiver. But we assume that this is already given and we'll just focus on the transmission. And of course, he was interested in telecommunications, telegraphs and telephones, and similar systems. So it made sense. I mean, all these systems already have a code. So he was interested in how can you transmit reliable information over an unreliable channel? How much redundancy do you need? And for that, it works beautifully. But and then it also has applications for encryption and for compression and for many other things. Like this approach, which we could call it objective information. But it seems that the questions that have to do more with living systems, and I would say also with artificial intelligence, have to do with meaning. And perhaps we're following a bit the path of Wittgenstein, that in his Tractatus Logicus Philosophicus that he wrote during the First World War, he was in the trenches. He basically developed, he was trying to develop a system for mathematical logic, and kind of trying to have everything within that system be consistent, and everything that doesn't fit in that system not to speak about it. But after some times, he became interested in education. Well, how humans, in particular children, learn how to speak. Let's say how natural language is acquired. And he enrolled to be a teacher in an elementary school. In his biography, it said that it was a bit like fight depression and to get away from temptations of Vienna, because he was homosexual and he frequented places where he could satisfy his needs, his sexual needs, but then he felt guilty about it. And I think in his family, 3 of his brothers committed suicides. He was also kind of with a suicidal tendency. So with help from one of his sisters, he thought, okay, I'll go to a small village to be a teacher, also like a therapy, but also because he was interested in learning how children learn. So after some years there, he later was, I forget whether Cambridge or Oxford, I think Cambridge. And he gave lectures, and some of his students kind of took notes from his lectures. Alan Turing attended one of his courses, and Turing was trying to convince him of the use of logic, and Wittgenstein was not convinced. And also, I was told of an episode where Karl Popper, also from Vienna, but also in the UK, he was giving a lecture on positivism or something, and Wittgenstein just stood up in the middle of the lecture. Oh, that's language game, and rushed out of the room. And Popper wrote his main work. I forget the name of this book of Popper, just as a response to Wittgenstein, which of course didn't satisfy him. But what I'm getting at is that later Wittgenstein, in let's say what we can read in his philosophical investigations, which were published posthumously, he advocates for let's say much more pragmatic approach to language and meaning of language. And for Wittgenstein, for many others that follow his ideas, the meaning of information is given by the use we make of it. And of course, that's subjective. I mean, the same information can have different meanings in different contexts. And I think all these measures of information that have been proposed are necessarily contextual, because they are still assuming that we all agree on the code that's behind. And I mean, I agree with this question being one of the big open problems in artificial life, and I think not only artificial life. I'm not sure whether it will have a solution, because perhaps this is related to the same limitations of formal systems that we've spoke about. That I mean, the first two proved by Gödel and third by Turing, that formal systems are incomplete, inconsistent, and non-decidable, which were, say, part of the Hilbert problem, the Hilbert lists of trying to make mathematics bulletproof, and it turns out that they aren't. So if you don't have all of this with formal systems, then I think this limits with contextuality, you limit how much you can generalize about anything. And this limits whatever you want to study that has to do with meaning from a formal perspective. But I mean, that's my view. Maybe I'm mistaken. And should be developed further, because it's kind of my intuition so far, but it's very probably I should better frame this more formally to show that not only, oh yeah, I have this idea, but say to present these ideas more systematically.
Yeah, it's a difficult and interesting question. I think we need to develop new mathematical tools that allow us to describe, for example, semantic information or the meaning of context, right? In fact, the Santa Fe Institute podcast has a couple of episodes about that. I'll put it in the chat. Thank you very much.
Yeah. Well, also, there's a book by Yuval Portugali and Herman Haken on semantic information theory. There have also been several attempts to try to bring meaning into information theory. But again, none has been, say, widely accepted. Irun Cohen from the Weizmann Institute also has some in this direction.
Thanks for the recommendation.
Yeah. So Domingo Islas writes in the chat, the article is very interesting and leaves many questions. Most important is how we conceive life and what its ingredients and particularities are, and how it is that when trying to recreate life with human technologies, we find ourselves with the problem of understanding it and activating the emerging mechanisms that sustain life. I also find it interesting how this concept of life can be used for its recognition in other bodies of the cosmos. Let's say the area of astrobiology has been growing. I remember 20 years ago, in my first day life conference, there was a talk by Charlie Lineweaver, and he spoke about astrobiology, and for me it was like, it sounded to me like a bit far-fetched, but in these 20 years, it seems that the questions that they're asking have been refined and better framed, and also the tools that they have developed are a bit better. And of course, it's not trivial to detect life from light years away. And I already told you this story about the Soviet probe to test whether there was life on the moon. That failed to detect life on Earth. But for example, right now what's the name of the current rover on Mars? It's not Opportunity, but well, the latest NASA rover on Mars, he's trying to find traces of life. Maybe because the evidence for water is already well accepted, that there used to be flowing water on Mars millions of years ago. But I mean, perhaps you might remember, or perhaps you were too young. In the 1990s, there was a big press conference because some NASA scientists announced that they had found what they thought it was a fossil of a bacterium in a Martian meteorite. So a rock from Mars that's somehow landed on Antarctica. They looked at it under the microscope. They thought, oh, that looks like a bacterium. Well, a fossil of a bacterium. Therefore, there was life on Mars. And of course, it was a huge commotion because, oh, there was life on Mars. But then many people were skeptical about it, and it was shown that that structure, that organization could be very well formed without organic reactions, without organic chemistry. And Sarah Walker, who is an active member of the astrobiology community, was telling me how they are doing these experiments on how to detect, let's say, the composition of atmospheres of planets orbiting not so distant stars, checking whether there might be signatures of life. And the problem, she was telling me that many of the complex atmospheres that have been found can very well be produced by inorganic chemistry. So you don't require like life to have complex molecules, let's say. So what they are doing now is not so much to try to find life, just like, okay, there is life or there isn't life, but they're taking a more nuanced approach, like, okay, the probability of this planet having life is whatever percent. And this allows them to to navigate these ambiguities that, okay, we detect this atmospheric composition in this planet, and it might be produced by life, but most probably it's produced by inorganic chemical reactions. And in some cases, there might be a 50-50 chance of life producing that atmosphere and, let's say, inorganic chemical reactions producing that atmosphere. So yeah, it's very interesting. Since we published this paper, so which year was this? 8 years ago. I mean, there hasn't been major advances in soft A life or hard A life. I mean, there have been some advances, but it's nothing spectacular. But on wet A life, there have been very interesting things. So I think we already mentioned protocells, and there have been interesting works about the active droplets. So let's say it's like a drop of I forget which chemicals, and they are on a substrate, and then there's chemical reaction, and they move to space, or they have dendrite-like appendages, or in some cases they dance around. Some cases they split. So let's say people are finding that these droplets are able to do things that we until recently thought that only living systems were able to do so. We are seeing that you can achieve this behavior chemically without lives. So that's interesting. And another thing that I believe we've mentioned already is the Xenobots, developed by the group of Michael Levin at Tufts and Josh Bongard at Vermont. Last week, there was a series of seminars organized in Japan. I forget the name of the Crossroads Labs, if I'm not mistaken. I should paste the link to the talks. So, the first talk was by Michael and Josh. So they told like the story of Xenobots. So these are biological robots, we could say, made up of embryonic frog cells, but they are doing things that they were not evolved to do. I mean, they are hijacking the mechanisms of these cells to build these xenobots that move around, and then they gather cells to build other xenobots. So they're already reproducing in a limited way. So that's something very interesting that has occurred in recent years. And very probably in the next few years, the tendency will continue that there are the space for breakthroughs in software and hardware. I don't think it will be that much, but in way-to-day life, there's so much more to explore. Of course, it's the most difficult one, and in some cases the most ethically problematic. But yeah, it's kind of giving us a different view of what life is and how to consider what it is. Any other comment? Which kind of robots you would prefer to take over the world? The AI ones or real life ones? Well, at the end, there's a blurry line. I mean, there's no like, okay, artificial intelligence ends here and only then artificial life begins. Especially when we are interested about applications, then the precise, let's say, concepts or methodologies behind whatever we are building are secondary. We just want systems to work. So if we call it machine learning or artificial life or behavior-based systems or whatever, that doesn't matter. So about the future, I mean, already for quite some time, I don't know, maybe 25 years or more, I've been saying that the future with artificial intelligence or with our technology, it's not so much that machines will take over the world, but that the tendency is towards greater integration with our technology. I mean, actually, our technology is what defines our species, and not only our species. All let's say many other species have technologies, but in particular, our species has distinguished itself because of its use of technology. I mean, considering fire a technology and agriculture a technology and electricity a technology and writing a technology. Yeah, I mean, without our technology, we wouldn't be human. And as our technology advances, then also our capabilities advance. But they have, I mean, our technology has always been a part of us, but they're becoming more and more relevant part of us, in the sense that we are becoming more and more dependent. But I mean, we were dependent on electricity already for a century or more. We are dependent on cars for 50 years or more. Well, yeah, I guess for most people. But we're dependent on agriculture already for millennia, and we are dependent on smartphones for a decade only. But yeah, we are becoming dependent on all these technologies. But we could say, oh, we are becoming enslaved by our own technology. And in a way, yes, but also we are able to do things that we were unable to do without this technology. So in a way, they give us superpowers at the cost of our freedom, whatever that is, because also concept of freedom becomes very ambiguous. But anyway, the tendency is towards an integration rather than competition between technology and humans. First, because we cannot separate them. We are becoming more dependent and more integrated with our technology, but also vice versa. Our technology is dependent on us. This idea that robots will become fully autonomous and decide that they no longer need us it doesn't seem plausible, not in the near future, but for me, because of the limitations of formal systems that I already mentioned. But anyway, making similar analogy with artificial life, whether what might be the future, I think that around the Human Genome Project, there were many discussions about what would be the future of our species now that supposedly we were able to control our genes. And if you watch this film Gattaca and other futuristic sci-fi films and books, you can get different versions of such a future. And I mean, with technologies like CRISPR, we are able to manipulate genes in a much more precise way. Thanks to this, we have some of the vaccines that have been successful against COVID-19. But yeah, I mean, how will the control of biology or molecular biology and genetics on one hand, and on the other with artificial life, whether we create new forms of life. Of course, there are risks that, let's say, some change that we make propagates and causes lots of disruptions. And because of that, many people they take a cautionary principle in the sense that you don't just develop because it's interesting, but you try to go slowly to value the risks and try to mitigate potential risks and understand what might be the consequences of developing different technologies. So let's say already this idea that, oh, we will be able to design, to genetically engineer superior humans is crumbled down. First of all, people didn't try to do it, or most people didn't try to do it. Perhaps in China, some people did it, but it was not very well seen because of ethical issues. But once we began to understand better how genetics work, it seems that in principle, yeah, you could, I don't know, choose the color of the eyes or some other particular aspects that can be more or less easily determined by one or a few genes. But most traits are very complex in the sense that plethora of genes and environmental factors affect them. So of course you can reduce risks of certain diseases, and there are few diseases that have very few genes or one gene that determines whether you will have that disease or not, or whether you will have a risk of developing that disease or not. But it's not so easy as like, let's say, going to the supermarket and say, oh, I want these traits for my child, and then you'll just get them. It's much more complex than that. So because of that, it's also limited how much we can control. And there's a recent book by Philip Paul. I forget the name of the book, but it's precisely about genetics and the latest technology that allows people to reprogram cells. So you can take skin cell and then to reprogram it to become neuron, and then you can have like mini brains from your own cells. I mean, the idea is to try to build organs from your own cells for transplant. So if someone needs a kidney transplant, instead of waiting for an available organ that might or might not be compatible, you basically build the organ in the lab and you implant it, and that could save, I wouldn't say lives, it could prolong for a few years lives of many people. So yeah, that's an active area of research. Of course, it's slow and it has limitations, but there's many interesting things coming. Amari, did you want to say something else, or your hand is still raised from the last year?
In my opinion, in the future, we will no longer distinguish between humans and machines. A small proof of this is our cell phones, which we can be thought of as an extension of our thoughts. And in addition, if we want to continue using computers without damaging our ecosystem so much, we must seek to minimize energy expenditure. I think a good option for this is neuromorphic computing. It's a new approach based on our brain, and creating technologies based on biological systems in general, I think could accelerate the machine-human symbiosis.
Yeah, our demand for energy consumption is increasing drastically. So I think something like 10% of all energy of the planet is consumed by the internet, which is huge. I mean, considering how much tons of cargo is moved all around the world, planes and ships and trucks and everywhere. I mean, it's huge. And agriculture, it's also a big chunk. But even when we develop, let's say, cleaner energies or less polluting energy sources, it seems that our demand for energy is increasing faster. So yeah, it is difficult to say, okay, we will consume less energy because almost everything we do requires energy. Of course, many things have become more efficient. So, example with light bulbs is very clear. When I was a kid, light bulbs were 40 watts or 100 watts. Now with LED bulbs, they are, I don't know, 6 watts or 8 watts. I don't know, the similar brightness. And we might say, oh, then you cut fivefold energy consumption. No, because since now it's cheaper, or let's say you can illuminate much more with less power, then you want to illuminate everything. And it's similar like when before electricity, when people had candles, and let's say depending on how much money you had, it was the amount of candles you could consume per night. But let's say then electricity came, and then we were able to light more. But then you want more and more and more and more. And in many places, in the night you have almost daylight quality. And with ERCO, you feel that because, for example, in United States, in the summer, inside buildings, it's very cold, so you need to put some clothes on because outside is hot. But then in the winter, they put on so much heating that you need to take off everything. So what I want to say is that inside buildings, in the winter, it's warmer than in the summer. Because, let's say, because we can. So if it's not with a prohibitive cost, we are gladly paying to have more energy just for our own comfort. And you can see this in the pictures of the Earth at night, where you can see public lightning reflecting to the sky. And already like 20 years ago, you could see that Europe and South Korea and Japan and many other countries were very bright. And this is because, for example, in Belgium, where I studied a PhD, there they have public lightning in highways. So it's not only in cities. So all the highways, they have public lightning, 3 a.m. morning. There are no cars driving, but all the lights are on because it's safer, because they can pay for it. And as energy has become more available, not necessarily cheaper, then more people want the same. So now you see these pictures from the night, and Mexico, it's also very bright. Well, Latin America, parts of Africa, and Asia, and only the poorest countries, like, for example, North Korea, where you can see a huge contrast between North and South Korea. You see that they don't have this, let's call it waste of energy, because of course, reflecting light into the atmosphere, it's pretty useless. But yeah, I guess that maybe with the climate emergency, there might be some change to our consumption habits. So, for example, you can see this with water. If you don't have water scarcity, even if it's expensive, well, in Mexico City, it's very cheap compared to Europe or United States. So we easily waste water. But in places where water is very expensive and very scarce, like Australia, they have developed mechanisms to save water in different ways. So you don't water your plants during the day. You try to recycle water in your house. For example, there's some installations where the water you shower with goes to reservoir that you can use for the toilets and things like that. So the moment that a resource becomes scarce, then we begin taking care of it. So probably it will be the same with energy. I don't know, since we have such a growing demand for it and we are developing technologies to satisfy that demand, I'm not sure.
Yes, I think we are in an era full of challenges. Let's hope to survive. And thanks again for the feedback.
Yep. Anyone else? Okay, so then I'll see you on Thursday.
Thank you very much. See you on Thursday.
See you, Professor. Thanks.
Thank you.
Thank you.
Professor?